Here are solutions to homework set number 2 for ECE 341 Random Processes. This homework set looks at combinatorics. Now in the previous lecture we looked at enumeration. One way to calculate odds is to list out every possibility and count how many are successes. Sometimes that's just not practical. For example, in bridge you deal out 52 cards. Well, you shuffle a deck of 52 cards and you deal out 13. So the number of possible hands is 52 choose 13. In this case, order doesn't matter. When you're dealt your hand a bridge, you can shuffle the cards around, usually by suit. And shuffling just kind of means that the order doesn't matter. You can rearrange them. That gives you 653 billion different hands. Way too many to enumerate. Well, still, you can calculate odds. If I want to know what's the chance of getting 6 cards of one suit, that's actually really good in bridge. There's a thing called trump. If your suit is trump, it beats anything else. So you want to have a lot of trumps in your hand. If you have 6 of them, you're pretty excited. The odds of getting 6 of one suit is as follows. There are 4 suits, choose 1, say hearts. There are 13 hearts in the deck, choose 6. Then of the cards that aren't hearts, that'd be 39, choose 7 of them. So the total's 13. Gives you 105 billion different hands that have 6 of a suit. The odds of being dealt one of those hands then is just the ratio. The number of successes over total number of hands gives you 16% chance. So there's a 16% chance of getting dealt 6 cards of one suit. Does happen fairly often. Note this also includes chances that the other 7 cards could be 7 of one suit, but we'll just go with it. Okay, problem number 2. Chance of getting 6 face cards. That's the Jack, Queen, King, Ace. Again, in bridge, the highest card wins, so Ace beats King, King beats Queen, Queen beats Jack. So one way to determine how good your hand is you count. Aces are worth 4 points, Kings are 3, Queens are 2, Jacks are 1. And if you have 13 points, you probably should be playing. You should be able to name trump. So the odds of getting 6 face cards would be there are 16 face cards in the deck. Choose 6 of them. There are 36 cards that aren't face cards. Choose 7 of them for a total of 13. 66 billion different hands have 6 face cards. The odds of being dealt a hand like that is the ratio 10%. Now, one way to check your answer is to do Monte-Carlo. Monte-Carlo is a way to sit there and get this to show up. Say, can I deal out one hand of bridge? So if I do that, here's what the program does. I'm going to take a deck of 52 cards, shuffle them. That's what this set of code does. Deal out 13 cards. So the first 13 cards are my hand. I then determine what the value of each card is and the suits. In this case, I just care about the suit. I will then count how many hearts, how many clubs, how many diamonds, how many spades I have. Sort in descending order. If the highest frequency is 6, I've got 6 of a suit. And the second part is checking for face cards. So if I have an ace or a Jack, Queen, King, add 1 to n as well. Add 1 to face cards, or add n, or increase n. If I have 6 of them, increase this counter. Then when I'm done, display how many times I got 6 of a suit, how many times I got a face card. So when I run this on my computer, well, if I could do that for one hand, do that for 100,000 hands. 100,000 hands takes 2.68 seconds on my computer. 16,000 of them were 6 of a suit. 10,000 were 6 face cards. Dividing by 100,000, my sample size, that's 16% and 10%. And note with Monte-Carlo, every time I run this, I get a different answer. It is random. So these aren't the exact odds, but they're pretty close. That's kind of a sanity check. If I did my calculations right and my program right, these two should match up. And they're not exact, but pretty close. So probably my calculations are right. Probably the program's right. Not a guarantee, but at least they're consistent. So that's the first set of problems. The next ones look at 6-card poker. In 6-card poker, you take a deck of 52 cards and deal out 6 cards. What are the chances of getting a full house? Now, a full house can happen 2 different ways. I can have 3 of a kind, 2 of a kind, and an off card. I could also have 2 3 of a kinds. So what I do in 6-card poker is I throw out 1 card, leaves me with a full house. The first one, I've got 3 X's, so there's 13 values, ace through king. Pick 1 for X. There are 4 X's, choose 3. There are 12 remaining values, pick 1 for Y. 4 Y's, pick 2. Then for the remaining, there's 44 cards, pick 1, or I could say there's 11 remaining values, pick 1. For the value, 4 cards of that value, pick 1, which is also 44, pick 1. Total is 164,736. That covers this combination. The second one I need to add in is 2 triples. That'd be, since these are the same frequency, I've got to do 13, choose 2 for X and Y. For the 4 X's, choose 3. 4 Y's, choose 3. 1248. Add the 2 together. There's a total of 165,984 different ways of getting a full house. The total number of hands is 20 million. So take the ratio. That's your probability. And kind of note, we did enumeration in homework set number 1. That matches up. And they should match up. Problem 5, the odds of being dealt 3 of a kind. That'd be XXX ABC. Again, these can't match. If they do match, that's a full house. So there's 13 values. Pick 1 for X. 4 X's, choose 3. A, B, and C have the same frequency. So 12 remaining values. Pick 3 for A, B, and C. 4 A's, pick 1. 4 B's, pick 1. 4 C's, pick 1. Total is 732, 160, which is matches up with what we did in homework set number 1 for enumeration. Although quite a bit less painful. That's the beauty of combinatorics. I don't have to sit there and list out every possibility. And this took about 30 minutes to do on my computer. Calculations took a couple seconds. To check your answer, I can go back to MATLAB and do a Monte-Carlo simulation. So here, I'm going to play 100,000 hands. For each hand, I'm going to shuffle the deck of cards and deal out 6 cards. Then find the value in the suit. Suit, I don't care. Count how many ones, or how many aces, how many twos, how many threes, sort in descending order, then check. If the most frequent card, there's 3 of a kind, and the second most frequent is 2 or 3, I've got a full house. If the most frequent card is 3 of a kind, and the second most frequent is less than 2, I've got 3 of a kind. That's for one hand. Repeat 100,000 times. So when I do that 100,000 times, that takes 3.2 seconds, and I get 808, 3590, which matches up. I'm taking the odds times 100,000. Enumeration said 815. I got 815. Well, calculated 815. Monte-Carlo was close. 3 of a kind. Again, same ballpark. I'm going to get a different answer every time I run the Monte-Carlo. So here was 808, 860, 797. Sometimes I get lucky, sometimes not. But this kind of gives you an idea of what the range ought to be for the calculated values. If you're wondering, well, once I have all these different readings, what do I do with them? That's a t-test. That comes up during week 4. So we'll cover that later. Finally, this is the nasty problem on the homework set. What are the odds of getting a full house in 6-card draw poker? So this is 6-card draw poker. You're dealt 6 cards. I can discard any ones that I want, draw and replace them. So let's use the following rules. If I'm dealt 3 of a kind, I'll draw 3 cards. If I'm dealt 2 pair, I keep the 2 pair and draw 2 cards. If I'm dealt 1 pair, I'll keep the pair and draw 4 cards. If I have no pairs, I'll keep 1 card, draw 5. So with those set of rules, I can actually calculate the odds. Calculating the odds is actually really hard because when I discard, say in this case, discard 4 cards, there's only 3 A, B, C, Ds left in the deck. So when I draw cards, I have to keep track. Is this an A, B, C, or D, or is it a different value? That makes it really hard. What I'm going to do is change the problem slightly. A trick in engineering is if you have a hard problem to solve, change the problem. Make it easier to solve, but keep the flavor of the old problem. So what I'm going to assume is when I discard cards, rather than throwing them away, I'll shuffle them back in the deck. That doesn't change the odds all that much. It does change the odds, but not a whole lot. But what it does is it really simplifies the calculations because now all the other cards, there's 4 of them in the deck because I shuffle these back in. So my answers will be slightly wrong, but close. Let's see. So if I'm dealt 3 of a kind, I'm going to draw 3 cards. So if my first cards were XXX, ABC, again, these don't matter because I'm going to throw them out and shuffle them back in the deck. So I've got 3 X's. 2 different ways of getting a full house is I can't draw an X because that'd be 4 of a kind. I can draw 3 Ys, that'd be full house, or YYA. So the first one is there are 12 values left. Again, X is already taken. Leaves 12 values for Y. 12 values, pick one, choose one. 4 Ys, choose 3. The second one is there's 12 values, pick one for Y. 4 Ys, pick 2. 11 values that aren't Y or X, pick one. 4 of those, pick 1. Multiply it all out, there's 16 different ways of getting a full house, given that I was dealt 3 of a kind. The total number of ways I can draw 3 cards is 18,240. Take the ratio, 17% chance of getting a 3 of a kind, of getting a full house, given that I was dealt 3 of a kind. The conditional probability then would be probability of A given B, probability of B. Take this, multiply by the odds of getting 3 of a kind, and I get 0.006, or 634 in 100,000 hands. First possibility. Second way of getting a full house. I was dealt a 2 pair. In that case, I throw out 2 of them, and I draw an XY, XC, or YC. Assuming these are shuffled back in the deck, then this would be there are 2 X's left in the deck, pick 1. 2 Y's left in the deck, pick 1. For the second one, there are 2 X's, pick 1. 44 other cards, pick 1, because again I shuffle back in. For the Y's, 2 pick 1, for Y, 44 pick 1. Add them all up, there's 180. I have 4 cards in my hand, all the rest are shuffled back in the deck, leaving 48 cards in the deck, because again I shuffled them back in. Pick 2, choose 2, 1128. So 15% chance of getting a full house, given I was dealt 2 pair. The number of ways of being dealt 2 pair is this one, 12% chance. Multiply the 2 together, multiply these 2 together, and this is the chance of getting a full house, given that I was dealt, or going through the 2 pair route. That should happen 1985 times in 100,000 hands. Third approach. I was dealt 1 pair. In that case, if I have XX, the other cards are shuffled back in. I can get that by being dealt X, Y, 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 or X, Y, Y, A, or Y, 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 A. So the first one is there's 2 X's, choose 1. 12 values for Y, choose 2. 4 Y's, choose 3. The second one, 2 X's, choose 1. 4 values, 12 values for Y, choose 1. 4 Y's, choose 2. 44 other cards, pick 1. Last one, there are 12 values, pick 1 for Y. 4 Y's, choose 3. 44, pick 1. Add them all up, 8544. The number of ways of drawing 4 cards is, since I shuffled back in, there's 50 cards in the deck, pick 4. Take the ratio, 3.7% chance. Ways of being dealt 1 pair, 48% chance. Multiply the 2 together, 1.8%, or 1801 in 100,000 hands. Finally, high card. This is basically the odds of being dealt a full house times the probability of being dealt no pairs gives you 0.28. So adding them all up, I should get 5517 full houses in 100,000 hands, or 0.55% chance. If I run a Monte Carlo simulation, and here's what that looks like. I'm dealt 6 cards. I then sort the cards based upon value, sort them based upon value. So I put all the kings first, then queens and jacks. Sort by frequency. Put the matching cards first, then the 2 of a kinds next, and so on. Then determine how many so what is n? Then check what kind of hand I have. I think I'm missing something. If it's a full house, if it's 3 of a kind, I draw 3. 2 pair, I draw 2. High card, draw 1, and so on. Then check to see the frequency of each suit, aces, kings, queens, after I draw, and see what kind of hand I have. If it's a full house, I count it. So that's kind of how the code goes. So with this code, every time I run it, I get that many full houses. Kind of matches up. I'll do this one right here. And also to debug my code, I kept track of how many full houses did I get, given that I was dealt them initially. How many times did I get a full house starting at 3 of a kind? How many times did I get a full house starting at 2 pair? Just to check my code, each of these ought to match up. And they're a little bit different, but pretty close, telling me that I think my code is right. Not positive, but it looks consistent. So it's roughly 0.57, 0.56% chance of getting a full house and 6-card draw. So that is homework set number 2. Kind of note, the nice thing about combinatorics is it really simplifies calculating odds. Sometimes it gets really unwieldy. In that case, you can use Monte Carlo. If I can play a single game, play 100,000 games, and count how many occurrences you get, Monte Carlo is not exact, but it kind of gives you a ballpark what the answer should be. And together, that would be combinatorics. Homework set number 2.